Now, in this video, I want to discuss the statement of the simultaneous saturation proof and really importantly, the definition about when you are in a simultaneous saturation system, because this is what you need to be able to prove to be able to use the simultaneous saturation theory. So this comes in the paper at the start of section 1, and we need to set up a framework for being able to discuss these simultaneous saturation systems. So here we start to put in some actual details about where our operators are mapping from and to. So I'm going to start with my operators Tm. I want to map them from a Hilbert space into a space of functions where I'm able to evaluate at points. And that's rather important that I be able to evaluate at points. Now, coming from a Hilbert space is going to allow me to set things up so I have a valid energy matrix, which has all the positivity requirements that I need. In a lot of practice, you would be using this for, say, LP theory, where you don't have evaluation. In those cases, you will usually regularize with some kind of modifier to produce an approximation which could be evaluated. So you have these operators, and X is just some non-empty set. And we'll see what the conditions put some kind of requirements on X to make sure that all of our system requirements are met. So I'm going to define operators Tm of P. And so this is just the operator Tm evaluated at the point P. And I'm going to consider that one to be a map from the Hilbert space into the complex numbers. Okay, so I'm thinking of this as some kind of evaluation map. Importantly then, if I take the dual of that, so TMP star, this maps from the complex numbers into the Hilbert space, and then I can form a TT star operator. Now this TT star operator acts from the complex numbers to the complex numbers, and so it is effectively a multiplication operator. So we quite often cheat a bit and just refer to it by the complex number that represents it. So that's what I mean when I say like the absolute value of this TT star thing, I mean in the absolute value of the complex number that represents it. So the first thing we need to do is define what it means to be a simultaneous saturation system. So a number of different parameters in here. The first one is lambda. So this is a parameter that is attached to the system, and it's the way we measure size. So lambda is something bigger than 1, and it measures what is big. Lambda inverse measures what is small. So this allows us to compare relative sizes of objects. So then I have M operators, T1 up to Tm, and I require the following things. So firstly, I require a trivial estimate for the TT star. Okay, so for any P and Q, I can take TT star and bound it by Bm squared. Now, Bm is not meant to be a difficult thing to obtain. This is meant to be a fairly trivial estimate that just captures the worst possible behavior. Okay, so this is like our sup norm. Okay, so B for bound gives us the sup norm. And then B without the subscript n is just the average, the geometric average of those. So now we need decay conditions. So the decay conditions say that for each one of the operators, I have some kind of dichotomy. So either TMP, TMQ star decays, or there's some condition that has to be met. And the way you should understand this is if I have this estimate here, TMP, TMQ star is bounded by R of lambda, that's saying that this decays and that I cannot simultaneously saturate at P and Q. Okay, so this is my condition where those 2 points cannot constructively interfere with each other. On the other hand, I could simultaneously saturate at them, and that's encoded in the condition. So this condition, it should be a symmetric relationship between P and Q, and reflexive because you always will be able to simultaneously saturate one point with itself. So the condition and the conditions we're looking at this paper are, for instance, geometrical, about how things sit in n-dimensional spaces. But we can state this very generally. It's just some condition to avoid decay. The final bit, which is very important, and it's usually the thing that takes the most proving, is the non-degeneracy. So non-degeneracy says that I cannot satisfy all these conditions in one go. So if I form a loop of points P1, P2, P3 up to Pn, each connected by one of these conditions, and they have to be distinct conditions in the loop. If I have this distinct loop, the only way it could be satisfied is the trivial loop, where all of the things are the same, and that the loop degenerates in other cases. So if I had a loop like this, where they were non-trivial, then one of these conditions would have to break. And so that gets you the simultaneous part of the system. So this is what we need to set up our system, and this is the sort of the group of objects we'll be dealing with. So then we'll move to what the major theorem says. The major theorem is telling us about, if we have one of these simultaneous systems, how can we measure some kind of bound on how many big numbers of big points we have. So I suppose that I can pick one function, or one tuple of functions in this case, and n distinct points for which I can make this large. So these are large points for the same function. So that's this lower bound here. If I evaluated each one of these points, my product is large, and it's equally large for all of them. So that gives us a sense of how large they are. And of course, one needs to compare L and B. So B is the subbound, L is how large these specific points are. Then I also assume I have some kind of a priori bound on N. So what this is just checking is that lambda tells us whether we measure with things are big or small. And R of lambda tells us the rate of decay. So it just says that N is sort of in the right kind of scale to be controlled by that rate of decay. And if all of that holds, then I can control the number of points in terms of B on L. I lose a factor of epsilon here if R lambda is not 0. If R lambda is 0, so I have not only just decay when my condition 4 fails, but my TMP, TMQ star is 0, then I get to get this estimate without the epsilon loss. So it's just, and we'll see in the proof why that's the case. So this is the main sort of thing that you will use. And when you're doing a simultaneous saturation proof, you pick up the bounds, the stop bounds you have for the trivial ones, then you compare them to the set of points of sort of size L. Now, there's a couple of points that I wanted to make about this. It may look like, for instance, that you could just put a whole heap of points in really, really close to each other, and surely they would have to simultaneously saturate, right? So if you just zoom in and put all of the points in really close, why do they not fall under this theory? And it's because of the loop condition. So if you come back up to this loop condition, it says that I can obtain the relation, and either the relation holds or I have decay, and then I have my non-degeneracy of my loop. Now, if I put all of the points really, really close together, in some kind of uncertainty principle setup, if they're too close together and I cannot determine whether they do or do not obey the relation, I can't have this non-degeneracy of the loop. Because if 2 points are really, really close to each other and they're indistinguishable in the framework that I'm working in, then I cannot say that this loop only collapses when can only work when it collapses to all of the points being the same. So there is built into this definition about a simultaneous saturation system some kind of background uncertainty principle that says that if I'm going to construct a simultaneous saturation system, I actually have to put my points a little bit far away. And what a little bit far away is going to be determined by lambda. And we'll see that multiple times, where we have to put a little bit of space between the points and obey an uncertainty principle.